we've got. I'm very happy to be here. This is really a fun session and conference. So this talk is about what words mean and how we understand them in context. It's a pretty short talk, so I'm just going to jump straight to the theory, and hopefully over the course of the talk you'll start to see why that theory becomes useful in particular interesting examples that are at sort of the intersection between, well, philosophy and psychology and linguistics. So Grice, as most of you know, had a research program on understanding language understanding, and it was based on the idea that language was an action. Saying something was an action that's taken. He has this quote, "One of my avowed aims is to see talking as a special case or variety of purposive, indeed rational behavior." So in the decades since Grice, a lot of people have built on this idea, and they've realized rational behavior in a lot of different ways. So what I want to tell you about is the way that I and some others have been approaching this, where we draw on the mathematical framework of Bayesian decision theory as a way of capturing what it means to take a rational action. So at its start, it's very simple. You simply say, look, there's a probability that a speaker, we call him S1, will make a particular utterance given the state of the world that he knows. And it's simply proportional to e to the utility of that utterance in that world. So far that doesn't really say anything beyond there's some function u that describes how good an utterance is in a particular world. So to capture the Gricean idea that people are being actually helpful, cooperative, we add first a very simple utility that says that the utility is actually something that's based on the belief updating of a literal listener. So this is the probability that a literal listener will guess the correct world given the utterance. We take a log to turn it into units of information, so that's kind of minor. And then finally, in order to fully specify that, we have to say, well, what does the literal listener do to update their beliefs when they hear an utterance? And we simply say, the literal listener starts with their prior beliefs about what the world is. They multiply by this delta function, which says, look up the denotation of the utterance, see if it's true in the world, and if so, you're good, otherwise cross out that world, and then renormalize. So this is a Bayesian updater who's assuming the utterance is true. And boom, now we have a model where there's a speaker who's taking a rational action in order to be informative, to provide epistemic help to this notional literal listener. So what we've done is basically realize Grice's main idea and motivation, but instead of appealing to a set of Gricean maxims to capture the constraints of cooperative and rational speech, we've captured that in the form of a utility function. That's nice because it starts to make quantitative predictions, which I'll show you in a minute. Before I show you data, let me just show you, take a brief detour and talk about this literal meaning thing that we need. So in the formulation on the last slide, we have a pretty standard truth functional denotation, this brackets u thing. And really you can think of that as being derived from a compositional semantic, something that Montague or David or Angelica would be very happy and used to seeing. It takes the utterance and it derives a function from worlds to yes or no. We could, in principle, relax that and say, well, it doesn't have to be a function that says yes or no to each world. It could assign a number. How good is this world for this utterance? It was straightforward to revise the model. We just say, okay, now there's a function. The utterance is a function that takes a world and gives you a real number. We multiply the prior by that real number, and then we renormalize. So this is just a softened version of the same notion of semantics. We mostly haven't done this over the years because it wasn't clear it was useful. But recently, we kind of stumped ourselves until we decided to try this again. So the context was these very simple reference games. So on the left, you can imagine being a listener. You see this set of objects. You get a little chat window where you can talk to the speaker. Maybe you say, hi, which object are we trying to guess? And then the other person is the speaker over here. They see the same set of objects, the complementary chat window, but they have one of the objects selected. That's the target. And so they type back whatever they want, and maybe they type back something like, the target is the little orange fish. It turns out that a referential expression like that, little orange fish, is very typical of what people do. But if you start to think about it, it's kind of puzzling, because in order to pick out this object, all you need to say is fish, right? And so in a rational speech production kind of story, it seems basically impossible to get that people should add extra words that aren't necessary to pick out the referent. And this notion of over-informative generation for referential expressions has a long history. I'm just pointing to one paper by Albert Gatt, but there's many people who have worked on this. And you could look up all of Albert's co-authors. So this is a problem for the basic Speech Act idea. So people do tend to produce over-informative referring expressions. With deterministic meanings, the rational action approach can't explain that. However, if you assume that the meanings actually are not deterministic, but they're a continuous value, what that means is that, for instance, in this situation, if you say dog, you have a small chance that dog will be misinterpreted as not dog, or that this will be interpreted as being a dog. And so if you add extra terms like, a scary-looking dog, that then is redundant information which is useful for decreasing the probability of miscommunication. So once we make the very small move of relaxing the meaning to be a real number, all of a sudden this thing that was called over-informativity is not over-informative, it's actually rational redundancy. So we wanted to test this. And in order to test this, we were going to have the same kind of reference game settings where we manipulated how close the distractors were in terms of category distance to the target. We needed some number to plug in, though, for this continuous value of literal meaning. So we went back to ancient history, 30 years ago when people were thinking about category typicality. We did a norming experiment where for every target object and every noun, we simply asked, how typical is this object for a table, for a dolphin, for a, etc. That gives us a number, which we rescale to 0 and 1, for the connection between the noun and the object. And we just take that to be the literal meaning, the denotation. It's kind of nice because the extreme cases do what you want. People will say that this is very atypical as a bear, so you get sort of 0, which acts like false. And it's pretty typical as a table, so you get close to 1, which acts like true. But there are other things which are kind of atypical tables that will have intermediate values on this measure. Okay, so we take those typicality ratings, we plug them into the denotation, and then we can get model predictions where we systematically vary how close the target and distractors are. I won't go through all of the details here. And the moral of the story here is that if you just look at the conditions, the sort of how close the distractors are to the target, the people in the model say that you should be over-informative more when the distractors are closer and less when they're farther apart. And the nice thing is that these predictions by the model are there only because the model is able to say adding some extra words provides a rational form of redundancy. In this case, it's not just extra words, it's also, it could be dog versus pug versus animal, so it's also the level of description. More satisfying, this is a scatter plot showing model predicted probability versus the empirical data, and this is not collapsed across items, so this is the incredibly messy and actually pretty sparse raw data. And you can see that there's a very good correlation still between the actual production behavior of people in this experiment and the production that the model thinks is the reasonable productions to identify the referent. Okay, so takeaway from this is two things. One, this what's actually a fairly simple rational production model is not a bad model of people's production, at least in these sort of games. And two, it requires relaxing the semantics to something that's a little bit more continuous in order to capture the idea that redundancy is useful. Okay, so let's move on from production to comprehension now. So this was what Rice was mostly after, thinking about how a reflective listener would interpret an utterance if they believe the speaker is being a rational speaker. And we can capture that in a very straightforward way. We simply say that the listener is a Bayesian belief updater who's going to update her beliefs from the data that they've observed appearing in utterance. Critically, the generative model that they have of the utterance, where they think the utterance came from, is a model of a speaker who's a rational action, rational utterance selector. So this simply says that there's some prior beliefs about which world we're in, we assume that the utterance came from the speaker choosing what to say, and that's the rational speaker from a couple slides ago. And then you renormalize, and that's Bayes' rule, and it says, okay, now I have posterior beliefs given the utterance. Just to point it out, this is actually a fairly complex model, even though it looks like one simple line, because this model refers to the S1 speaker model, and then the S1 speaker model refers to the L0 literal listener model, right? So there's this kind of social recursion, I think that you think that I think going. My co-authors and I have, for better or worse, called this the rational speech acts model, because of the idea that the listener thinks of the speaker as choosing approximately rational speech acts. And I wanted to point out that it's very related to a bunch of work in game theoretic, pragmatics, and linguistics, going back to Greek and many other people. There's an interesting intellectual history there that I'll skip. So you can use this model of comprehension for a lot of the interesting but standard phenomena, in particular scalar implicature. So you can capture things like some is interpreted as some but not all, except when it isn't, for instance, when there's only partial knowledge from the speaker. You can capture behavior of both adults and kids in terms of these ad hoc scalar implicatures, like my friend has glasses. I don't want to tell you in any detail about any of that. There's a lot to say, but it's not as exciting to me as where I'm going next, which is to say, there's a small catch to this model so far. Namely, the pragmatic listener has to imagine a particular speaker in order to interpret an utterance. But if you think about that a little bit, it may often be that the pragmatic listener is not sure exactly what kind of speaker they're hearing from, right? So what should you do when you know that you're getting an utterance from a helpful speaker, but you're not sure exactly what kind of speaker that is? Well, as a good Bayesian, you should just do a joint inference. So here I'm writing theta to represent all of the speaker-specific information that you might have. So this simply says, okay, the probability of an utterance from a speaker depends on the world, and also which kind of speaker that is. There's maybe some prior over kinds of speakers, and then you do a joint inference of the world and that kind of speaker. Okay. It turns out this is a very small change to the model when I write it like this. It turns out it has huge, profound, and interesting consequences. And the consequences depend on exactly what aspect of the speaker you lift in this way and reason about. So in work that I won't tell you about today, we've shown that you can introduce and lift a topic, or QUD, and that gives rise to non-literal language understanding like hyperbole and metaphor. You can lift the prior, this POW aspects of the background knowledge, and that seems to give rise to some presupposition, projection, phenomena, although there's a lot of work to be done still on that. What I'm going to talk about for the rest of today is what happens when you imagine that that speaker might mean something in particular by a word and you're not sure exactly what. So if you have uncertainty about the details of the lexicon, the details of word meanings. So let's dig into that. And I'm going to dig in by switching gears a little bit and reminding you all about this crazy class of words called vague adjectives. So vague adjectives are adjectives like tall that seem to refer to a degree along the scale. And they're interesting because they have three properties of, that are kind of characteristic of vagueness. So the first thing about vague adjectives is they're class relative. So a tall building is totally different than a tall man. And that already tells you that there's something kind of squirrely and interesting with the meaning of tall. It's not self-contained. It depends on at least the things it's composing of. The second thing is that there are borderline cases. So there are people who you would not agree that they're tall and you would not agree that they're not tall, or just, I don't know, they're right in the middle. I'm charitably putting myself in that category. Probably not. Finally, there's this great classic paradox going back to ancient Greece, the Sorites, paradox of the heap. And here's a particular example of it. The Sears Tower is a tall building. How many people agree? Okay. A building half a meter shorter than a tall building is a tall building. How many people agree? Okay. And all buildings in Chicago are tall. How many people agree? Okay. I got two people with big grins on their face. So the puzzle here for me, there's a couple of ways to think about why this is a puzzle. One is normatively, like, what should our logic work like given this paradox? But the interesting part for me is the psychological puzzle of what is it that people are doing when they agree or disagree, such that they are very happy to endorse the first two premises here, but they very firmly reject the conclusion, which seems to follow from mathematical induction. Right? So we started thinking about this, and we first went to what's basically standard lexical semantics for adjectives, scalar adjectives. So just assume that there's some scale. So for tall, the scale is height. And it would be reasonable if you figure out whether the adjective is true or not by simply comparing to some threshold along that scale. So you say, okay, that boy is tall if he's taller than a meter. Great. This, by the way, is a useful semantics for explaining a bunch of compositional semantics details, which is what people like Chris Kennedy were using it for. And it feels like it could be explanatory about the interpretation of adjectives if we knew how to set the threshold, which we don't. So the idea here is, well, let's just treat the threshold as one of these unknown but inferred aspects of how this speaker uses language. So, you say to me, Bob is tall, and I think, okay, I don't know exactly what you mean by tall. There's some threshold you're using, and I'm going to have to infer it while I interpret this utterance. Okay, so formally, you can basically say, let's let lexical items introduce free variables. It's a very standard thing. Montague did it, Lewis did it. So that the semantics is underspecified. And then let's lift those free variables to be resolved by the pragmatic listener. Okay, so basically all I've done is change the original RSA model, rational speech X model, by introducing this theta variable, which is inferred at the pragmatic listener, and it's passed down, and it's used here in the denotation function in whatever way you want. So that's all it does. It just gets inferred by the pragmatic listener and used in an appropriate way by the denotation. And for us, for the adjective tall, it's simply providing the threshold of comparison. Okay. So if we take that model and then we look at the posterior inferences when you just hear Bob is tall, you get interesting behavior. So this is a kind of a simplified example just to show you what the model does. So the black curve here is the assumed prior distribution over heights. So people are about 0.5 tall, but with some normal distribution. The yellow line is the distribution over the prior distribution over a threshold, so it's uninformative. You have no idea how the speaker is going to use this adjective tall a priori. The interesting thing is the red curve here, which is the posterior distribution over heights after you hear tall. So you've inferred that the person is taller than the a priori, the average, not maximally tall, but pretty tall, 1 or 2 standard deviations. And that's basically because there's an effect of the pragmatic reasoning where when figuring out where you should put the threshold, you don't want to put it too low because then it would be an uninformative utterance to say tall, and we think that speakers are trying to be informative. You don't want to put it too high because then it would be very unlikely to be true, and we think that things that the world is like, the prior matters in determining what the world is like. So instead you put the threshold in sort of a happy medium in the middle where it's informative but not implausible. Okay. How does this help with the Sorites? Well, in terms of this schematic, imagine that's the Sears Tower. Imagine that's the building half a meter shorter than the Sears Tower. So this is the part of the distribution over thresholds where the shorter building will still count as tall. And as you can see, that's most of the probability mass, right? So it is going to be not probability 1, not certain, but very likely that the slightly shorter building is still tall. And that goes through even if you don't have a particular known height to start with. So you say, condition on B being tall, take a small epsilon and ask whether B minus epsilon is still bigger than theta. And as long as epsilon is small, that will be true with high probability. So the idea is that the inductive premise is not valid. It doesn't have probability 1, but it has very high probability. It's a very reasonable conclusion. Okay, so we wanted to test this. First, we had to get the actual prior knowledge for some domain. So we elicited the prior distribution over prices of a bunch of objects, coffee makers, headphones, laptops, sweaters, and watches. And then we took those prior distributions and plugged them into the model. Then we had the target judgments, which were both the simple usage of gradable adjectives. A watch that costs $3,000 is expensive, agree or disagree. And then the inductive Sorites premise, a sweater that costs $8 less than an expensive sweater is also expensive, agree or disagree. And we systematically varied the category and the prices that were in each of these utterances. So on the left, what I'm showing you is the concrete premises, the model prediction versus the mean human data. And you can see, first of all, the model predicts the human data very well. And second of all, it's accounting for the differences between classes. All of the different colors are more or less on a line. Watch is maybe a little bit screwy. And second of all, there's gradation, including these borderline cases in the middle where people don't want to either agree or disagree. The model captures that as well. On the right, I'm showing you the behavior for the Sorites inductive premise. And so when the epsilon is small enough, people are happy to agree to that premise, and the model says that they should be happy to. Interestingly, as the epsilon gets bigger, a watch that costs $1 million less than an expensive watch is expensive. No. And so both people and the model start to say, no, that's not nearly so good a conclusion. Okay, I'm out of time. I wanted to flag, so the basic idea here is we're leveraging the idea that there's an underlying scale and that the semantics could be a very simple scale, which only looks complicated because of the pragmatic inference. That idea can be exported to a lot of other words and other domains. So my graduate student, Michael Henry Tesler, who's around here somewhere, has some really excellent data and work on generics where we do exactly the same thing, assuming that the underlying scale for the generic is the predictive probability of the property given the kind. Here's just here's the beautiful slide showing you that the model is able to predict the data. And critically, it predicts the data even for a bunch of philosophically puzzling cases like mosquitoes carry malaria. Fortunately for you all, even though I can't describe it, there's going to be a poster on this. So please go to Michael Henry's poster to hear all of the amazing details about generics and habituals. It really is the last thing on Saturday, but this will encourage you to go. It's such a great poster. Okay, I'm out of time. The basic takeaway here is that there's this formalized notion of uncertain Rational Speech Act interpretation. The U is for uncertainty about the speaker. That provides a quantitative theory of how language is interpreted in context. Kind of, in some sense, formalizing the Bayesian notions, but in some other ways, refining and doing new things. And I only showed you one example, but I believe that this kind of approach is really fruitful for a lot of these philosophically interesting cases because we can get a lot of leverage from very simple semantics undergoing complicated interactions with prior knowledge and reasoning about the speaker through the joint pragmatic inference. Thanks.